Hello, I'd like to show you how to use the AGGIOS EnergyLab tool to estimate and measure power for a Xilinx ZCU102 evaluation board. I will then also show you how we optimize power consumption using the AGGIOS Seed firmware. The ZCU102 evaluation board features a Xilinx UltraScale MPSoC, specifically a ZU9EG chip. If we take a look at the monitor, here we can see the EnergyLab tool in action.
EnergyLab is an integrated development environment for creating and analyzing power models of your system based on the IEEE P2415 UHA standard. EnergyLab is also used for configuring and generating the seed firmware for your target. On the left, we see a choice of different views of the model. By default, it's a view of the system hierarchy. I have already loaded a model of the ZCU102 system, so this is what we can see here in the central area. We can see the board at the top level, which is a Zynq UltraScale MPSoC, along with other board components such as the DDR4 SODIMM. If we take a closer look at the Zynq SoC, we can see the different power domains and the complete subcomponent hierarchy, including processors, buses, memories, and peripherals. The IEEE P2415 UHA model contains all the power-related details relevant from a software and system developer's point of view. In addition to power states and their respective power models, it also covers transitions and latencies, and most importantly, the dependencies. Dependencies between different components, as well as dependencies on the clock or voltage trees. Incorporating dependencies ensures that during simulation only states are entered that are feasible in a real system as well. The UHA model can easily be extended to cover your particular configuration, from custom FPGA components and application-specific peripherals to a complete custom board or system. But aside from modeling the hardware, EnergyLab also lets you model your software as UHA tasks in order to accurately reflect your application use cases. A task expresses the software's dependencies on the hardware as well as on other software such as operating systems or middleware. The use case we are looking at here is software-defined radio, which requires the device to be in the lowest possible power state most of the time, but then quickly wake up when a valid signal is detected. We have created tasks such as transmit and vocode here, which depends on Linux being active, but also requires, for example, the cryptographic accelerator to be on. EnergyLab lets us follow the dependencies via hyperlinks, so we can quickly jump to the Linux OS task, where we can see that it includes a large number of hardware dependencies reflecting the Linux configuration we're using. Now that we've modeled our system, we are ready to start the simulator. This brings up the EnergyLab simulation window. The EnergyLab simulator UI is organized like a debugger. On the left we see the scenario file, which essentially is a sequence of timestamps and events. Using the control buttons in the toolbar, I can either single step or run to the end or until I hit a breakpoint. You will notice that our plot area now shows the computed energy profile for our use case. To get more details, I can view the top consumers in my system, I can zoom in, I can view transition latencies, or details about a particular component. EnergyLab has many features that make it easy to optimize power for your system and use case using UHA models. But now I'd like to show you how we can apply such optimizations to the actual target device by configuring and generating a customized seed power management firmware. The seed configuration dialog allows me to choose from various optimizations, either globally or individually, where I can enable features such as frequency scaling of the AXI bus or DDR controller, letting devices enter optimized idle states when unused, or by scaling the voltage of the main supply rails. It essentially allows me to enable complex power optimization features from a user-friendly UI. Seed also offers helpful diagnostic features that help troubleshoot power-related problems, such as more verbose prints, latency measurements, temperature reporting, as well as the Seed console, which allows you to interactively determine the state of any component, clock or reset line, helping you identify optimization opportunities on your actual target for your application. Finally, I will go ahead and generate the firmware. This invokes the standard Xilinx toolchain, and once it's done, we get our custom firmware ELF binary, which we simply need to include in our boot.bin file for our SD card.
Let's now take a look at the Xilinx ZCU102 evaluation board. On this board, EnergyLab can measure detailed power consumption for each voltage rail. All we have to do is to connect a USB UART cable and then connect EnergyLab. To start the application, I'll insert the SD card, including the generated Seed software, and then turn the board back on.
Now we can click on EnergyLab's Test and Measure button up here and connect to the USB port of the MSP430 system controller to start the power measurements. The power consumption is plotted in the main area here, and we have the terminal windows at the bottom. You can see the Linux prints on the left, as well as prints from Seed and the real-time processor on the right. The power plot shows the power of each power domain, but we can also drill down to show the individual voltage rails of any domain. The power plot also shows the temperature reported by Seed, measured using the Sysmon device on the SoC. Once Linux completes its boot procedure, we can start the software-defined radio application. The system immediately enters the deep sleep state. Signal activity will wake up only the real-time processor, which validates the signal. Once a valid signal is detected, the Linux subsystem is woken up. This is where the signal processing is performed. As soon as the signal transmission is completed, the system goes back into the deep sleep state. Whenever Linux wakes up, you can see the latency reported here, just a little over 60 milliseconds to resume Linux, which is more than twice as fast as without Seed. Using the optimized Seed firmware, we are able to run Linux below 1 watt in the active state, while still meeting the application's latency requirements when coming out of the deep sleep state. Overall, the Seed Power Management firmware has reduced the power consumption of the system by nearly 700 milliwatts in the active state, by employing a variety of optimizations, including, for example, dynamic AXI bus frequency scaling, as well as DDR frequency scaling, as summarized on this chart. At the same time, the latency optimizations included in Seed allowed our application's latency requirements to be met when coming out of the deep sleep state.
I hope you've enjoyed this video. If you'd like to learn more about EnergyLab or Seed, please consult our website at aggios.com. Thank you for watching.